And I want to express my appreciation to the organizers for inviting me here to participate in this workshop. I have been thoroughly enjoying both the workshop. It's really been very educational, but also the city, which is quite unique and very beautiful. In fact, I want to take a moment to tell you how much I have been enjoying my stay here. Because I've always been a little bit self-conscious about my name, which is long and a bit difficult to pronounce. So for the first name, I shortened it to Tim. That's common in the United States. But I couldn't do much about my last name, which also includes this harsh X letter there. But in Basque country, it seems like every word has an X. I feel very much at home here. So. Thank you for the invitation. So I want to tell you today about recent work that we have been doing in the general area of two-dimensional materials, and in particular on Twistronics, and I'll explain what that means precisely. The last few years we have been blessed with a cornucopia of two-dimensional materials, some of them new, brand new materials, some of them older structures. So we have semiconductors, a variety of semiconductors, transition metal dichalcogenides, phosphorine, and the graphene, which is the standard metal, but also insulators, these interesting structures with 5 layers, and superconductors. Someone pointed out earlier that even the cuprate semiconductors are essentially two-dimensional systems. And one big question is, now that we have many of them in layered form, through exfoliation or other techniques, how to combine them. And I'm sure many of you have seen this kind of picture from the work of Gaim and Grigorieva, suggesting that we can just stack one layer on top of the other. This is a little bit misleading because the layers don't quite fit nicely as Legos do, and that's one of the big issues that I will try to address. So the usual materials that we deal with, and they're very common in applications, are graphene, the standard metal, the zero band gap, the family of transition metal dichalcogenides, which have different structures, slightly different structures, but also different compositions, and in different layers they also exhibit different band gaps. And finally, hexagonal boron nitride, which is a very nice insulator, very wide gap, and very chemically neutral. People have been able to put different layers on top of each other, as suggested here by molybdenum disulfide on top of tungsten diselenide, and you can barely see these here, but in early experiments about 2013, Philip Kim's group was already reporting how they would make contacts with these and make devices out of them and explore the rich physics of these structures, including interlayer excitons and many other interesting phenomena. What made these structures particularly interesting in the last few years is the ability to put one layer on top of another, but with a small twist angle. And here are some examples: graphene on graphene, molybdenum disulfide on molybdenum disulfide, also from Philip Kim's group. There's a very intriguing, ingenious technique that the experimentalists figured how to use in order to put one layer on top of another with great precision. So basically they take one layer of graphene, tear half of it so they know the exact relative orientation of the two halves, then twist the upper half and reposit it on the bottom layer, and then they encapsulate it on with boron nitride to keep it nice and clean and smooth, planar, and they make contacts through the edges and make very nice devices. So several groups have reported this kind of technique and making structures with this kind of technique. What's really amazing is that they can control the relative twist to better than 1/10 of a degree, which is really quite impressive. So recent work by Philip Kim's group again shows this kind of pattern, and what you see here is what is called dark field imaging. This is used by using scanning transmission electron microscopy, and you see these nice patterns produced by this twist over very large areas of order microns. So what exactly is happening here? Well, once you include this twist, you produce a moire pattern, as you see sometimes in shirts when presenters in TV wear shirts that have patterns slightly offset from the pattern of scanning of the image. And this is basically what's happening here with the two layers on top of each other. You see regions where the patterns almost align, then they're misaligned, and then they match again, and in between regions. But all these regions have very interesting features now. So these are two graphene layers in this example, and you see in red the AA regions where one layer is exactly on top of each other. The two layers, the top layer hides the bottom layer. There are other regions in between which are called AB or BA, and in these stackings, in these regions, the top layer hides half of the atoms of the bottom layer, and you see the other half of the bottom layer atoms in faint yellow here. And it's important to note that the AA regions are the high energy regions. The two layers do not want to be in this configuration, whereas the AB or equivalently BA regions, those are related by symmetry, are the low energy regions, so the structure wants to be in this configuration. And this plays an important role. So what would you expect in terms of Brillouin zone and reciprocal space symmetries from this arrangement? Well, you have a hexagonal Brillouin zone from the top layer, let's call this the blue one, and another hexagonal Brillouin zone from the bottom layer, that's the red one, and they're slightly misaligned, and that produces a supercell Brillouin zone, the black hexagon, so you have a much smaller effective Brillouin zone with the center here and the corresponding high symmetry points. And of course, with each original hexagonal Brillouin zone of each individual graphene layer, you have this set of Dirac cones associated with it, with these Dirac cones at every corner of the hexagon. And now we have, of course, two sets of Dirac cones, one of them from the red layer and the other from the blue layer, and those are at each corner of the effective Brillouin zone, the supercell Brillouin zone. The interesting physics that comes out of this can be captured in a simple picture, and I must give credit here to Alan MacDonald and his co-workers who were the first to point out this interesting physics. And it comes from the fact that in this new now supercell Brillouin zone, you have the two sets of Dirac cones, and the Dirac cones will intersect, as shown here, with the dashed blue and dashed red lines. And at the intersection points, you have degeneracies which will split into bonding and anti-bonding configurations, as shown here. This energy scale, the difference from this point where the two Dirac cones intersect in the positive energies and here in the negative energies, this energy scale is set by the moire pattern, by the length scale. It's only the length scale or the angle of twist that tells you how far these two intersections of the Dirac cones are. But there's another energy scale, which is the interlayer hybridization, how much the layers interact. And that energy scale will determine how much these degenerate points split, both here and here. And it's the interplay of these two energy scales that makes the physics very interesting. So the bands will also bend differently near the K points because of this splitting. So the Fermi velocity will also be renormalized. And this is all captured by the simple picture that originally Bistreitzer and MacDonald put out. And if this is true, then you would expect near the Fermi level, the neutrality point, to see these kinds of density of states. And the slope here will be much different than the slope of the original density of state associated with individual graphene layers. So here are some early experiments from the group of Pablo Jarillo Herrero, showing what is happening if you have a twist angle of 1.8 degrees, and you do indeed see these two humps. So you can think of this diagram essentially as showing you the density of states. The horizontal axis here is the level of doping, which simply corresponds to moving the energy, scanning the energy around the charge neutrality point. So you can think of the horizontal axis as the energy, and the vertical axis is conductivity, which very closely reflects the density of states. So this is exactly what would have been expected, including gaps here separating these two humps associated with the states near the Fermi level. And this was explored at great length by Pablo's group, and we contributed to this exploration, including details of how the off-diagonal conductivity behaves, Hall effect measurements, and so on. Now, what really made things very exciting was the discovery about a year ago, a little over a year ago, that you can actually get superconductivity in twisted bilayer graphene at a very specific angle, which was called the magic angle. So if you twist the two layers relative to each other by about 1 degree, a little more than 1 degree, you get superconducting behavior, it's actually a very strange superconducting behavior for the following reason. Now, this diagram is basically related to what I showed you a moment ago, but more complicated. So these two here, this is the one hump below the charge neutrality point, and this is the other hump corresponding to the single particle bands associated with these splittings that I just showed you earlier. And this shaded region here and the other shaded region on the other end correspond to the band gaps that separate those bands from the rest. However, what is really amazing is that you don't see a single hump anymore, as I showed you a moment ago. So this would be a single hump below the charge neutrality point, and then another single hump above the charge neutrality point. But you see more than one hump separated by mini gaps. And this was a big surprise because it implies that you don't have a band structure anymore that can be interpreted in a simple picture of non-interacting electrons. You have a Mott insulator. So this used to be a single band, which is now split into sub-bands because of the Mott insulator behavior. So these would be holes here, and this is the corresponding single band of electrons split into states separated by a small gap due to the Mott insulator behavior. So this was what was termed the correlated insulator behavior at half filling in magic angle graphene superlattices in one paper. And in a follow-up paper, it was shown in some detail that when you go away from these the mini gaps into doping the system this way or that way, you get superconductor behavior. So the horizontal axis is again the carrier density or doping level, or just simply scanning the energy around the charge neutrality point. The vertical axis here is the temperature, and you see at what temperature you need to cool the system in order to obtain the superconducting behavior. This is at 1.16 degrees of twist. This is at 1.06 degrees of twist. The scales are a little bit different, so here is where you get the highest superconducting temperature, roughly 1.5 degrees or so. So this was all quite exciting, and it generated a lot of interest in this system. In fact, not only it is a superconductor, but it is a high temperature superconductor par excellence. What we mean by this is that if you scale the system's features appropriately, that is, if you scale by the Fermi temperature, you find that so the horizontal axis is the Fermi temperature and the vertical axis is the critical temperature. You find that for this system, which is shown here by this bright red dot, the critical temperature as a fraction of the Fermi temperature is quite high. This blue shaded band here includes all the conventional high temperature superconductors, including all the copper oxides and so on. To put it in a different way, if you plot again the ratio of the critical temperature to the Fermi temperature, you see here this dashed line down here corresponds to the heavy fermion superconductors. This dashed blue line corresponds to the average of high TC cuprates. These dots are from measurements in different devices of magic angle graphene. The average is this line, and up here is the iron selenide single layer superconductor. So it really is quite high temperature measured in terms of the Fermi temperature, and that's because the Fermi temperature, of course, scales with the carrier density, and you have a very low carrier density because of the very large effective periodicity in the system. So how do we understand all this? Up to now, I've been giving you a simple interpretation and lots of experimental results. So in order to construct a detailed theory of this, you need to put some atomistic features and provide the relevant atomistic wave functions. But this is not trivial. So this is from a recent review entitled Magic Angle Graphene Reveals a Host of New States. And this is a direct quote from this article. For the time being, we only know that all the correlated states come from electron-electron interaction. That doesn't tell you much. And their ground states and their interaction mechanisms between these quantum phases remain a mystery. Moreover, I'm going to even challenge this later on. Okay, so very little is known because the system is so complicated and it's quite messy to extract a simple picture based on the atomistic. So nevertheless, the graphic is quite nice. So if you open one layer up, you see interesting patterns here, and these are suggestive of what the single particle wave functions might look like. They're not single one-site states. Okay, one major obstacle in describing these systems is the fact that all these relative twists produce incommensurate layers. So momentum is no longer a quantum number, and the big question is how to describe such systems. So the solution that we came up with was to use configuration space, and I'm going to describe this in fairly simple terms and give you references for more complicated descriptions. So here's the real space arrangement of the system, and again you see this kind of moire pattern. In some regions the two layers are on top of each other, in other regions they're very differently arranged. And your eye may fool you that this region is equivalent to this region, but it is not. It's very, very close. That's why your eye fools you that they're exactly equal, but they're not. And that's what we mean by incommensurate. But you can now go down to each one of these regions and identify the local environment that the atoms in one layer experience due to the position of atoms in the other layer. As I have illustrated here schematically, for this square, for example, you have this arrangement of red and blue layer atoms, and this corresponds, if you take as a reference point the origin of the red atom layer unit cell, then this corresponds to this much shift for this local arrangement. This local arrangement corresponds to a different shift of the second layer, this local arrangement to a different shift of this second layer, and so on. And you can generate all these local environments by simply shifting or rotating finite structures. So essentially, this boils down to using an integral over all these local environments. That's what's written down here. So this is an integral over all the possible local environments. And here you can have any kind of trace of physical quantities. And this integral replaces our familiar integral over Brillouin zone. You can replace the Brillouin zone by carefully sampling periodic structures by averaging over local configurations in arbitrary incommensurate structures created by these local shifts. So we had the good fortune to work very closely with a group of very talented mathematicians who actually developed this very detailed theory and published a series of papers explaining how this is done exactly. I'm not going to go into these kinds of details, but this is essentially what we have been using to do calculations in these general situation of incommensurate layers. However, as you must have realized, I'm sure, this implies a local Hamiltonian, a Hamiltonian of finite range. And of course, we know how to do this, so we can go from block states to a tight binding Hamiltonian through localized Vanier orbitals. As someone mentioned earlier this morning, I don't have to explain to this audience what Vanier orbitals are, and thanks to the pioneering work of Nicola Marzari and David Vanderbilt and collaborators, we have a tool to go from the block states to the optimal localized Vanier states. My students even use a verb to Vanierize. This has become a verb, the bands. And we indeed can claim that we have ab initio tight binding Hamiltonians essentially without any approximations other than deciding the range of the Hamiltonian due to this very powerful scheme. By the way, I should mention that my student Chang Fang is the one who carried out this work, and we published a series of papers with all the appropriate parameters, including the dependence on strain and so on. One interesting thing that we discovered is that there is an angular dependence of interlayer coupling in graphene, and you can capture that by looking at the appropriate Vanier orbital for graphene, which is not a simple PZ orbital. So this is the actual Vanier orbital that we produce. This is the PZ orbital with angular momentum 0, but you have higher angular momentum contributions, and if you include all these, you have a much more accurate description of the interlayer coupling. And indeed, you can have now two layers with filled circles and open circles at relative distances and twist angles and whatever you like. At each side of these layers, there's this more elaborate structure, more elaborate orbital than a simple PZ orbital, and the interlayer coupling has the dependence on higher angular momentum through these terms. And for example, the term labeled V3 is about 25% of the term labeled V0. So it's not trivial. These contributions are not trivial. And we are able to capture this and do calculations for twisted bilayer in graphene at an arbitrary twist angle. And this is an example. So we have on the vertical axis and also color-coded from blue to yellow the density of states. This axis shows the energy, and this axis shows the angle. And the energy is 0 here. That's the charge neutrality point. And as you go away from 0 angle to about 1 degree or so, you find all these features which are entirely new due to the relative twist. In particular, you see this very high peak here. So the density of states really shoots up at this very special angle. And that's why we decided to call this Twistronics. So you can really manipulate what is going on by controlling the twist angle. Actually, I feel a little bit of great affinity to this term because I came up with it and I suggested it to my students. They liked it, and we put it at the title of the paper. When I was a student, you had to be extremely careful what you put as a title of the paper because the physical review editors were extremely strict on what they would accept. I guess times have changed. So but this was quite popular and has been picked up by even magazines, and now it's being used quite widely. Twistronics tunes 2D materials properties and so on. So I'm quite happy to see this. It even has its own Wikipedia entry, and you can look it up. Okay, so using all this now, all this machinery, we can actually reproduce a lot of the experimental results. What you see here in this short movie is a scanning of the energy. As you go up and down in the energy scale, you have different constant energy contours, and these energy contours can easily account for the experiments that I showed you earlier, describing Hall conductivity and Landau levels and so on, and the jumps between the slope in the Landau levels, fillings and so on. So this is all very natural. It comes out directly from this type of calculation. So if you recall, this kind of experiment was at 1.8 degrees. The really exciting physics, the superconductivity happens at 1.1 degree, close to 1.1 degree. And here's a band structure for what happens there. And here's a density of states, electronic density of states, as a function of position in space, and you can see where the electrons are concentrated in this moire pattern. So here at the bottom is the moire pattern, and you see high peaks of electron density at the AA regions. So this corresponds to an AA region, this to another AA region, and so on. Exactly the high energy regions where I told you that the system doesn't like to be. That's actually where the electrons want to be for states near the Fermi level. And you see this other interesting feature, these so-called flat bands. The bands are never completely flat. They always have some amount of curvature, and this is important. I'll explain it in a minute. So this is another picture of the flat bands. This is a two-dimensional K-space, and this is the energy, and these are the flat bands, and this is the density, density of states now corresponding to the flat bands, and you see that they really are very sharp features related to these bands. By comparison, this straight line here, the purple line, corresponds to freestanding graphene, a single graphene layer, density of states multiplied by a factor of 1,000 to make it visible on the same scale. So these are really very, very special features. Now, one thing that we realized early on is the interlayer coupling plays a big role, and you can control it by pressure. For example, at 1.12 degrees, you have fairly flat bands. At 1.47 degrees, the bands are not that flat, but you compress the two layers by 5%, and the bands become again very flat. At 2 degrees, the bands are not flat at all. At 5% compression, they become flatter, and at 10% compression, they become again very flat. So you can control the magic angle, as in this diagram that we produced, as so this is the magic angle as a function of the pressure. And indeed, this was a nice prediction, because we predicted that at 2.2 GPa, the magic angle would be about 1.31 degrees, and experiment verified this soon thereafter. So the calculations can be quite accurate and realistic. Now, in order to gain more insight, several people have pursued arguments about the symmetry related to these states, the flat bands. This is a very nice work by the group of Ashwin Vishwanath and Sendhill and their collaborators. And they looked at the different shapes of the flat bands if you assume the breaking of different symmetries. So this is all very nice, but it's not quite adequate, because symmetry considerations alone cannot capture the whole story. In fact, a very big part of the story is the atomic relaxation, and I haven't told you much about that. So this is actually this is work that first appeared by the group of Elad Tadmor and collaborators, and pointed this very important feature out. So this is a picture of the different stackings, as I mentioned earlier, AA, AB, BA, and so on, without taking into account atomic relaxation. Now, they took into account atomic relaxation by using an interatomic potential and quasi-continuum theory, and this is the picture that you get after relaxation. The AB or BA domains, which are equivalent, expand significantly, because that's the low energy structure, and the AA domains shrink significantly. And there are the regions between them, which are called, in this paper, they were called saddle points. We also call them domain walls. And the behavior of these different features is quite interesting. Namely, if you plot here the rotation, the twist angle of the two layers when you try to put them together, and then on the vertical axis, you plot the local twist, the actual local twist of the AA regions. So you see that at relatively large angles, 2 or 3 degrees or so, the two are almost the same. So you twist the layer, and indeed the two regions are relatively twisted to each other by the same amount. But if you go to small angles, around 1 degree or less, you find that the relative twist is constant. No matter what relative twist you try to apply to the entire system, the relative twist in the AA regions remains constant. Moreover, if you plot again the size of the stacking region, that's the domain wall, or the AA region, the diameter of the AA region, that's the red line, and the blue dots are the size of the domain wall, then the two also become smaller and smaller at larger angles, but they become essentially constant at 1 degree or below. So these are the calculations of Tadmor and co-workers, as I mentioned, based on the interatomic potentials. We verified all these calculations using ab initio DFT calculations. I don't have time to describe this, but I just want to capture the results, which are exactly compatible, exactly the same as the results by Tadmor and co-workers. And these results say that at small angles, this is about 2 degrees, the different regions are all more or less the same, AA and BA or domain wall. So AA is red, ABBA is black, domain wall is white, so they all have roughly the same size. As you reach about 1 degree or so, things start to clear out, and at 1 degree and below, you basically have small AA regions connected by domain walls which have the same size, and the only thing that changes after that is the relative size of the ABBA regions, with the entire pattern being essentially the same. So this plays an important role. So here's another picture of the same result. A, B, and BA regions here are the depressions. That's where the two layers are closest together at the normal distance of about 3.35 angstroms. The AA regions are the places where the two layers are farther apart. They repel each other significantly, 3.6 angstrom separation, and in between are the domain walls. And this makes a huge difference in the band structure. So this is with relaxation. You indeed see these flat, isolated bands separated by band gaps from the rest, whereas without relaxation, everything is a big mess. So the atomic relaxation really is a key feature in making sense of the single particle physics of the problem. Moreover, by looking at this more carefully, you realize that we did a series of calculations at a lot of different values. You realize that it's not a single magic angle value, it's a small range of values that makes this happen. So this is a complicated diagram. I'm plotting several things at the same time. So for example, here I'm plotting in blue the width of the flat bands. So that's the blue line. In red, I'm plotting the gap separating the flat bands from the rest. And of course, there are gaps above and below. That's why you see a red line here and another red line here. And the dashed line here, the dashed black line, is the Fermi velocity, which should go to 0 at the magic angle. And indeed, all these features conspire to give optimal behavior at a small range of values near the magic angle, and if that were not true, I claim that it would be impossible to observe anything if you required truly a very special value. But it is a range of values. Moreover, Alan McDonald and co-workers introduced a parameter. It's hidden here. It's called alpha square, which is essentially the inverse of the twist angle square. And as a function of this, they plotted the Fermi velocity, and you see that the Fermi velocity goes to 0 at several points. So larger values of alpha correspond to smaller values of twist angle. And so they predicted from their simple theory that you would have several places where the Fermi velocity would become 0, the bands would be completely flat, and you would have this highly correlated behavior. What we find when we include full relaxation, the red line is without relaxation from our calculations, but with full relaxation, you only have a single minimum. So we claim that there is only one magic angle and a small range around it. So the million-dollar question, of course, is what are the states associated with it? With these flat bands. And again, here I think there's an intricate story, namely, these are the actual bands in black. In the different colors, I'm showing you projections of these bands into different localized regions. So the two sets that are shown in orange correspond to states that are centered at the AA regions. This is the total wave function. These are the wave functions projected in different layers, layer 1 or layer 2, and sublattice A or sublattice B. So if you concentrate on the total wave function, so these are two wave functions that correspond to AA regions. These are wave functions that correspond to the domain walls. And finally, these are wave functions out here that correspond to the AB or BA regions. And all of them are coupled. And as you change the angle, they switch character. For example, if the angle is slightly smaller than the critical value, so these states are related to holes in AA regions, whereas if the angle is greater than the critical angle, the nature of these states is switched and they become domain wall related states. So bottom line is that you need this manifold of states around the Fermi level, all of which are coupled and rehybridize as you change the magic angle. And the minimum number of states that you need to describe this accurately is 10. And that's from a single K valley. That's from one of the two hexagons of the two layers. So you have as many states from the other valley, 20, and if you include the spin, that's 40. So that's a lot of states. And it's impossible to do a Hubbard model with 40 states. So that's completely forget. So there's a lot of work currently going on, and we're working closely with Ashwin and his group to boil it down to even a smaller set of states, but this is highly non-trivial. A few words about work going on currently in my group. We're working on high throughput models where you have to construct a language and then automate the search for different situations which produce these interesting features. We're also looking at other materials, twisted bilayer molybdenum disulfide. You again see these high density of states, situations with localized states, lots of things to explore there. And more recently, we got interested in tri-layer graphene. So this is the picture that I showed you already, and I explained about bilayer graphene. This is tri-layer, 3 Dirac cones. Things are more complicated, and you get, again, these kinds of flat-looking bands in a simple picture. However, here you have two different and independent twist angles which you can independently control, and the size of the system is much, much larger. The reason why I started doing that is because there are recent experiments by the group of K. Wang at the University of Minnesota who suggest these are the superconducting domes again, and they suggest superconductivity in this system at significantly higher temperature, about 3.4 degrees. This is more than doubling of the original TC. So this is quite exciting, but doing the calculation is very complicated because you see here, so this is the pattern in layer 1, the pattern in layer 2, the pattern in layer 3, different patterns superimposed. So we call that a moiré of moiré, and it really gets very complicated. And just to leave you with one last impression, so this is the band structure for bilayer graphene at 2-degree twist. So this is the tri-layer with the coupling between layers 2 and 3 turned off. So you see roughly the same bands here from the bilayer, and the third layer produces a Dirac cone. So this is one particular scan along the Brillouin zone, the effective Brillouin zone. And this is now with the layer 2 and 3 coupling turned on, complete mess. So this is along this particular scan, the black line in the Brillouin zone. You can do a different scan along the orange line, and this is the scan along the same line. You see something looking like flat bands, like the simple picture, but there's all sorts of other bands interspersing, and they're not isolated anymore. So because of all this, we argue that even the simple notion that you absolutely need flat bands, and because of the flat bands and highly localized states, you have correlations, high correlations, this may not even be true. You may have more complicated mechanisms at play because this system is not dominated by flat bands. It's not this set of bands is not isolated from the rest, and it has much higher TC. So This is the first time I'm showing this because it's very recent results. We just finished writing the paper, and perhaps because it's so complicated, and perhaps because it was first described in a conference in the Basque Country, maybe we should call this Twistronics. So okay, so that's it. Thanks for your attention. Just a couple of words of acknowledgements. These are my students who did all the work, but many other people in my group were involved in this. And we had the great fortune to work very closely with two fantastic experimental groups, Philip Kim and Pablo Jarillo Herrero, as well as the group of mathematicians I mentioned, and several other theoreticians, colleagues. Thank you very much for your attention.
So thank you for this great talk. Any questions, comments?
So you showed us that this relaxation is very important of the structure. So how do you do these relaxations? I mean, because these are big.
Yes,
big.
yeah, very good point. Thank you for bringing this up. I didn't have a chance to describe this, but we can do very accurate calculations by using just DFT work. Let me see if I can find the appropriate picture here to illustrate this. Yes, here it is. So basically what we do is we take two layers, slide them in all the possible ways relative to each other, and that gives us an energy landscape. And the derivatives of that energy landscape tell us the local deformation that the crystal will undergo. So this is a very nice, actually exact theory in the limit of continuum elasticity. That's where we borrowed the ideas from, and we apply them here, and we get these patterns. So this is, for example, the energy as a function of the relative displacement, and this is the energy again for graphene. Red is high, black is low, and these are the AA regions, ABBA regions, and from this energy we can extract the gradients which tell us what happens to the atoms, and then we displace the atoms according to these local gradients, and this is the actual atomic pattern.
Nice talk too. So like most of the DOMs you show for the superconductivity, they look pretty much like cuprates, right? Like from the past. But then cuprates are a very controversial subject. So people don't know essentially what the main idea behind it is, either electron-electron interactions or electron-phone interactions. So looking at your plots and most of the results you show in your talk, it seems like you are more in the club of electron-electron interactions, mediate superconductivity, but I'm not so sure about it. Do you have any comment about it?
Yes, so in a sense, that's a good point. In a sense, there are a lot of similarities to the cuprates, but it's much more complicated because, as someone showed earlier this morning, in the cuprates we have a very simple lattice, a square lattice, with essentially one orbital per site. So you can do much more in terms of correlated physics, trying to describe the correlated physics in that simple system. Here, as I tried to explain, the lattice itself is more complicated, and also the orbitals, the individual single particle states involved are much, much more complicated. So in order to put this theory together, it's much more challenging. So it is similar, but also quite different, and richer in a way.
In the beginning, you showed this model where you have a tight banding with a higher angular momentum terms.
Yes.
Is this somehow a way to account for the relaxation of the lattice, or there is not accounted for?
No, this is not the relaxation of the lattice. This is the result of doing as detailed and careful work as we could do in order to produce the right Vanier orbitals. So this was a Vanier orbital. So it was the optimally localized Vanier orbital that could describe the band structure calculated from first principles essentially exactly. And that Vanier orbital was more complicated than a simple PZ orbital.
Because there is some more recent paper where they do something similar, accounting for the corrugation of the lattice, and then trying to map on a simple PZ model of tight banding.
No, this did not involve corrugation of the lattice. But it did involve motion of the two layers relative to each other so that we could capture the interlayer coupling at all the possible arrangements. And that necessitated this more complicated Vanier orbital.
Tim, did you find any connection, going back to the relaxations, can you find any connection with the theories of these commensurations of typically helium and graphite that Bert Halperin, Susan Coppersmith were working with in the 80s?
Yes.
Based essentially on theories of Frank van der Merwe and that kind of thing?
Yeah, that's a great question. To be honest, we have not explored that because we focused on looking at the electronic states that come from that relaxation. But that's a great point. Yes, that's, yeah.
Okay.
We should look into that, yeah.
He's your neighbor, isn't he?
He is, well, yeah.
Okay, any further question? So if not, let's thank Tim again.
Thank you.
So next speaker is Silvia Picozzi. She's going to talk about ferroics in two-dimensional materials.